So, new material down here. This is day 131, reflection and refraction working together. I need more light. I can't read that. Is that going to work? There, it works. And let's zoom in a little bit. Okay, here we go. Usually, whenever a wave hits a transparent boundary, you will see three different possibilities. You will see transmission. That means the photon goes through the material. That's what transparent means. Waves can go through. Or you will see reflection. When light hits a glass pane, some of it bounces back, some of it goes through, and then some of it is absorbed and the glass will get a little bit warmer. One of these actions will not be seen when the light hits an opaque boundary. Opaque means like a brick wall. You can't see through it. So which one does not happen? You do not get any transmission. Thank you. How do two-way mirrors work? The light from the interrogation room. Okay, so this is like you see on TV shows where you have somebody in a dim room watching through a glass window to the bad guy being interrogated. And the bad guy looking at this glass pane just sees like a mirror. But this person here can see through it to the other room. This is a dim light and this is a bright light. That's a key aspect to it right there. So, this is not because of some kind of a special film or a one-way street, so to speak, of the glass. It's because of this transmission, reflection, absorption stuff. Okay, light from the interrogation room hits the mirror. This from here. It is made of a glass that mostly reflects. Okay, so we have bright light. Let's say that we have 200 units of light that come down from the light bulb, and they all bounce off the guy's face. 200 units of light go this way. And let's say that 90% of the light that hits this glass gets reflected. So that means that 180 units get reflected back and 20 units go through. Okay, 90% reflects, 10% goes through. So the cop in the observation room sees what's going on here, but it's dimmer, like sunglasses, but they can see what's going on. The suspect sees reflection. His reflection. A normal person, if the bad guy looked at another cop, the interrogator, the detective in this room, he would see 200 units bouncing off of the interrogator's face. And so this reflection of 180 units is just about as bright as that. So it looks like just a plain old mirror. A tiny bit of the light from the suspect will transmit. I can't spell transmit. Transmit through. Transmit through. That's really sloppy. Sorry about that. Transmit through and be seen by the police. Okay, now let's look at the observer's room. The observer's room is kept very dim. The small bit of reflection and refractions coming from the policeman are covered up by the light from the suspect. So let's get a different color here, and let's say that we have, only 10 units of light coming from this light bulb. So 10 units of light get reflected from the cop's face and goes towards the window. Of these 10, 90% get reflected. So that's going to be 9 bouncing back. and 1 going through. Okay, so let's look to see what these two individuals are seeing. The bad guy, looking at the reflection, looking at the light coming from the window, 180 is his own reflection, and only 1 is from the cop. So this 180 is going to drown out the 1. It's going to outglare it, outshine it. So the bad guy doesn't really see the 1. This cop here, seeing light come from the window, 20 units are the light from the guy's face, 9 units are his own reflection. So he might be able to see a little bit of his own reflection there, but it's much dimmer compared to the light from the bad guy. So you'll see both images, both your face and the other, but the other is much brighter. Okay? The same can be seen in your home windows as you look out at night. Have you noticed that? You're sitting in your front room, you're sitting in your bedroom, it's nighttime, you look at your window, it's like a mirror. You might be able to see a little bit of action going out there, but mostly not. There's not much light coming through. It's like the dark observation room out there, and you are in the interrogation room. But then the exact same window during the daytime, during the morning, it's dim in your room. You haven't turned on the lights yet. It's kind of sunny out, so you can see the outside really well, but you know that people can't see you very well because it's dark in there. Okay. I have one of these glasses right here if you want to experiment with it. Okay, next. Rear view mirrors. How do they work? Now, it used to be that every single car had this kind of rear view mirror. And then it turns out they're turning fancy now, electronic. I'm talking about these kind of mirrors. I'll shine it here underneath the camera. Rear view mirror that goes up on the windshield as you're driving. It's the upper middle, okay? And there's this little flippy flappy thing here. If you want to have a dim setting, you flip it one way, bright setting the other way. How many people are aware of this little flippy flappy thing? Some people may not be aware of it, and that's understandable nowadays. Okay. For those of you that have it, how does this work? Once again, if you have it in one setting and you look at the car behind you, you can see its bright headlights. It's glaring off this. It shines bright in your eyes. It says, "Ow, that hurts. I don't like that." And so you flip the switch, and now the same headlights appear dim. That's what I'm talking about. Okay. Some cars don't have this kind of a feature. They do it differently. The night setting of a rear view mirror is designed so that the headlights behind you are not too bright for your eyes. Look at the illustration below. A silvered material coats the back of the mirror. Draw a thick black line on the back of the mirror and label it silver backing. Okay, so fill this, color this in dark. In case your printout is really dim, this is what the glass looks like. It is not rectangular slab. It's a trapezoid, and on the back is the silver backing. What do you think D and B stand for? Silver backing. We have D for dim and B for bright. Okay, so what's going on here? We have the headlights from the guy behind us coming in like this. The glass is a certain kind of chemical compound where the whole glass, throughout the whole glass, just a little bit of it is going to reflect. Some reflects this way, just a little bit, and so that's a dim image that goes right to your eyeball. Most of the light gets transmitted through the glass, and now it hits that silver chemical paint that you just gave, so it all bounces off that silver stuff. And so most of the light ends up bouncing off the silver, going up here and hitting your forehead. That's the bright setting. So with the little flippity flap, the little flippy flap thing down here that you push on, that tilts the whole mirror so that then the bright light hits your eyeball and the dim hits your nose. Yeah.
What color is the mirror?
It's transparent. One might say that the glass can have a slight green color or slight blue depending upon what kind of chemical makeup it is, like a stained glass window. But we're going to assume that this is going to be as clear as they can possibly make, which means no color at all. Okay, analyze. Number 9. Is the glass here made mostly to reflect or to refract? Most of it is made, it's made to mostly refract, to transmit. Does the flipping of the switch to daytime setting do to the mirror? It tilts it. Tilts to a different angle. Okay, so that's how that works. We have both reflection and refraction going on at the same time. With rainbows, we have the two actions happening at the same time as well. Label 5 of the boxes in the diagram with the letters from this list. Not all the boxes will be used. You choose which boxes are best to use. Okay, so first of all, letter A. I'm just telling you this is the notes. Here we have sunlight from all the colors coming in and hitting this raindrop. Letter B. Here we see some of the light reflecting off of the top left of the raindrop. But some, we're going to put letter C right here. Here we can see the light spreading out and slightly different shades going on here. That is to show that some of the light refracts into the raindrop and different colors refract to different degrees. And we start making the rainbow there. Letter D is right here. On the back side of the raindrop, the light reflects and it goes back in. Some of it escapes, but some of it's going to reflect as well. Letter E, light again passes the surface of the drop. That's right here. And refracts as it enters the air. Again, different colors refract to different degrees, separating away from each other even more. And so the person down here then sees the different colors spread out. Yep.
How do you know how to label them like ABC?
I'm just telling you that because it's easier for me to put A, B, C, D than to have you write out all of these phrases.
So we won't have a question like that?
No. Nope. This is just to speed up note processing, note-taking process. Okay. Fiber optic cables. We're going to speed this up here a little bit, and we're going to ignore the math problems right now. We're just going to say that when we have a light ray going from a diamond out to the air at a 10-degree angle, it's going to bend a little bit like that. This is going to be a slightly bigger angle. I don't know what it's going to be. I'm going to make up a number 12. When I approach the surface here from the diamond into the air at a bigger angle, it's going to refract even more. I'm going to make up a number, 24. I don't know what it is. And then, at a 22-degree angle, it's going to be even bigger. Even bigger. And at 33.38, it's going to be just skimming the surface. The exact numbers here are not important. The idea is as you approach the surface at a bigger and bigger angle, it's going to refract bigger and bigger until it gets just to skim the surface. And I believe this is that number for that. Okay, so what happens if you approach the surface at an even bigger angle? In that case, everything is going to reflect as if it hit a mirror. And this is going to snap immediately from 90 degrees, being right along the surface, to being equal angles here, just like hitting a mirror. This is called total internal internal reflection. When you have an angle bigger than the critical angle, your calculator is going to say syntax error, or just simply error. In fiber optic fibers, you can have either the sounds of your voice on the telephone, or you could have information from the internet converted into a code of flashing lights, like Morse code. And the lights are sent down these plastic fibers, and these little lights always hit at an angle so that it bounces completely on the inside and none of it escapes. So these little pulses of light can travel miles and miles and miles and miles all the way across the ocean. And we can transmit our communications that way. So, and the ocean cable, like this, it would bounce this way, and then it would bounce like this, and then bounce this way, and then here, and just keep on bouncing, not losing much of its energy at all. Light rays always hit the surface at angles greater than this critical angle, due to the thinness of the fiber and the fiber's density. This is true even if the fiber makes a turn around a corner. Thousands of conversations, thousands of web pages can be transmitted over a single strand the size of fishing line. Each one of these conversations, each web page that's being transmitted will have its own slight different color. In other words, a different frequency or a different wavelength. We perceive them as different colors. And this is what those fiber optic cables look like. Just like fishing line. And if I shine light down it, let's see here. Shining the light, can I see that there? Let me turn off the light here and see if that helps. Okay, I'm shining the flashlight down the thing and let's turn off some more lights. My flashlight is not very bright. Drat. Nope, it's not working here at all. My flashlight's not bright enough. So let's do it this way. Oh, do my phone. That's a good idea. Okay, let's get my phone out. Okay, there you can see. Can I see? There we can see sparkles, but not along the sides. The light is not escaping the sides, but it is escaping the ends. Okay. So we can imagine the on and off for each one of those little strands being a Morse code sending a message of some sort, web pages or voices. Alrighty. And that's the end, I think, of all the notes.